number 1. Over here is fastener number 2. Okay, so that's why you have to multiply by. So I'm just going, for simplicity's sake, I'm just going to call force resistance will be equal to 5 times 10 to the power 3 multiplied by 320 times 10 to the minus 6 divided by 333 times 10 to the power minus 6 divided by 2 multiplied by 0.1. Okay. So the force resistance of the fastener, 5 power 3 times by 3 to the power minus 6 times 0.1 divided by 2 divided by 3.333 is equal to 1.5 times 10 to the power 3 Newton. Okay. So this force, remember this force, right, that is applied if we draw an element, right? This force over here, right? And this force over here. So this is, if I were to draw our transformation, this is Y, this is Z. Shear YZ is equal to shear ZY, right? And we know that this will be equal to force divided by area. Whereas this over here, the shear stress is VQ over IT. Interesting, isn't it? One is the shear resistance of one plane is that formula. The other one is force divided by area. So the shear stress of the fastener is equal to 1.5 times 10 to the power 3 divided by the cross-sectional area of the fastener, which is what, 4 millimeters. Okay, so pi r squared. So 1.5 power 3 divided by, so it's equal to 119.366 times 10 to the power 6 Pascal. Okay. So this shows you, right, if you are going to design a structure like this, okay, you're going to design a structure like this, okay, based on the spacing that you have given, okay, you have to ensure that the screws or the fastener need to be able to carry a shearing stress of 119.366 times 10 to the 6 Pascal. So if I'm going to make a guess, you will try to avoid nails made of aluminum. Okay, you want them to be made of steel. Let's look at some practical application. Okay, you want some made of steel. Okay, you want to try avoid aluminum or copper. Okay, so these are how analysis like this will help you. Okay, but the most important thing over here, I think, is how to determine the first moment of area. It's always very confusing, right? So as I said, you have to know, right, where failure will occur first. Once you know where failure will occur, things will be so much straightforward. Let's look at another example. Now, the next example that I'm going to look, I'm not going to solve the whole problem, but I'm going to teach you how to determine the first moment of area, more important than any other things. I think if you see enough, get familiar with it, you should be fine, okay? Next is a very not difficult, but it can be confusing. Yeah, let's look at this structure over here. Example number 3. Right. So example number 3. There are two possible location of failure. Okay. So if we zoom in close enough, right? So failure, can occur over here, right? Or failure can occur over here. Yes or no? Right? So we know for the fact that the centroid will be over here. Hey, come on, man. We know for the fact that the centroid will be somewhere around here. Right? So this is the position of centroid. So we need to find the first moment of area. Okay. So if I were to divide this failure at the top, and then I'm going to call this bottom. Okay. So at the top, the first moment of area that we have to take is this area over here for the top. For the bottom, we have to take this area. Okay. Now, some of you might say, Eugene, why not take it from the web? Right? Why not take it from the web? If you take it from the web, right? If you take it from the web, you only need to calculate this small region. If you were to look at the web, which is wrong, right? The web, you only need to look at this small region, right? If the region is so small that when you calculate the first moment of area will be too small. Okay, that's why you don't. Then some of you might say, Eugene, why not we do this one at the top? Again, you can see the values. The value coming out will be very small for the shear flow. Okay, so that's why you take the shaded region. Okay, so let's look at the top. So before I go on, we want to look at the y value, the first, not the first moment of area, the so-called the centroid position. So the centroid position is 3.1 inch from top. I can be wrong, okay? I don't know whether they do from top or bottom, but I'm going to try, okay, from top. Okay. So more important is to calculate. I want to show you how to calculate the first moment of area. Okay. So let's look at top section. Okay. So the Q is equal, so the width is 12 inches. The depth is 1 inch. The Y bar is 3.1 minus by 1 divided by 2. So 3.1 minus by 0.5 times 1 times 12 is equal to 31.2. Yep, it's the same as the answer. 31.2 inch cube. Okay. So that is for the top section. Okay. Then for the bottom section, all right, the Q. So the width is 6. The depth is 1. The Y bar is 5677 minus by 3.1. Right, because 51167 minus by 3.1. 3.1 is from the top. This is 3.1. And then you do minus 1 divided by 2. Okay. So 7 minus 3.1 minus 0.5 times by 1 times 6 is equal to 20.4 inch cube. Okay. Again, it's calculating the first moment of area. Once you get this, everything is straightforward. This problem, again, you see there's 2 fastener, right? And over here, bottom part, there's also what? 2 fastener. Okay. Now let's look at something more difficult. Unfortunately, there always one. This is a straightforward example. So example number 4. We don't do simple problem for this course, unfortunately. Okay, now this one is tricky. Okay, this one is tricky. Okay. And I'll tell you why it's tricky. Okay. So again, how to take the first moment of area? Okay. And the centroid is 0.18676. Okay, so if I were to sketch the centroid, right, it's gonna be over here. Okay. So this distance to this distance is 186.76 inches. Right. So the question asks where, how, or what is the first moment of area to consider? Right? This is a very very tricky problem. Okay, this is a very, it's not impossible, but it's tricky. Okay, so this is one of the example that we have to break one of the rules. Okay, we have to break one of the rules, and I'll tell you why. Okay, so remember, if we have a shear force over here, okay, or we have a V over here, right? For a longitudinal shear, what they say? The first, the shear stress or the shear flow must distribute on the entire member. So what does this mean? This means the shear flow must flow all the way down. Okay, all the way down. So the first moment of area to take is this entire area. Now you tell me, Eugene, it crossed the what? It crossed the centroid. You're right, it did. Okay, but only the shear stress flow through the entire member, then it will transmit. So that is why the area taken is you have to take these two areas. Okay, you have to take the entire area over here. Okay, so now we will do the calculation now. Okay, so the first moment of area now is equal to Q is equal to twice, and the width is 25. The depth is 0.25. The Y bar now is 0.18676 minus by 0.25 divided by 2. Okay. So this is equal to 0.18676 minus 0.25 divided by 2. That's about 25 times 0.025 times by 2 is equal to 772 times 10 to the power minus 6. Meter cube, sorry. Let me do again. 0.18676 minus 2 times 0.25 times. Yep. Okay. So now, what does it want to calculate? We determine the shear force in each of the bolt. So this is a true bolt. Okay. So it's a double shear. So we know that Q is equal to VQ over I, and this is equal to force resistance divided by spacing.